Hey guys, welcome to my channel. I'm LeetCode, and today we have a great problem for you guys, right? So let's quickly go ahead and read the problem statement, all right? So the problem's called Coco eating bananas, right? So he says Coco loves to eat bananas, okay? There are n piles of bananas, and the eighth pile has pile of I bananas, right? So they're telling us that so we have an array of no numbers, right? So each index, right, represents a pile, right? And then the pile number at that pile, right, represents the number of bananas at that particular pile. Okay. The guards have gone, right, and will come back in 8 hours, right? So okay. It says Coco can decide her banana per hour eating speed of K, right? Each hour she chooses some pile bananas and eats K bananas from that pile, right? So if the pile has less than K bananas, she eats all of the bananas instead and will not eat any more bananas during this hour, right? So we eat all the bananas at that power, right? And we can't just go on to the next power in that same hour, right? We have to wait the next hour to go to that power. Coco likes to eat slowly, but she still wants to finish all the bananas before the guards return. Return the minimum integer k, right? Such that she can eat all the bananas within each allocated hour. Within 8 hours, right? So very interesting, right? So guys, how do we solve this? What's needed to solve this, guys, right? So we have our so to just recap everything, right? So we're giving an array of power. So we're giving n powers, right? And each power has uh x amount of bananas at that power, right? And we have a h hours, right? And we need to find the speed, the eating speed, right? That's a banana per hour eating speed that's of k, right? That's good enough to eat all of bananas, right? So and we want to return the minimum one, right? So there can be many different speed that's good, right? But we want the minimum one that's good enough to eat all of the bananas, right? So this is kind of the ask. Okay. So for this example, we see that giving this pile of bananas, right? And each number you see, right, is the number of bananas at that pile. And we have 8 hours to eat all the bananas, right? So this is interesting. Uh, so it so if we need to eat all the bananas within 8 hours, right? We need to eat at a speed of 4, right? Okay. That's what they found to be the minimum speed required to eat all bananas, right? So let's see if that's correct, right? So we see that we have 3. So eating at a speed of 4, we would only need to spend 1 hour here. Eating at a speed of 4, and we will spend the first hour, we'll eat 4 bananas, right? Which means we'll be left with 2. Let's make sure we keeping track of that, right? Okay, so that we don't forget. Okay, so we spend 1 hour in the first part, right? And we spend 2 hours. Second part, because we eat 4 bananas at the first hour. In the second hour, we eat another, uh, we eat 2 bananas that's left, right? Because, right? Which means we spent 2 hours there. And then the same concept here, right? We would eat 4 bananas, right? First hour, there's 3 left, right? And then we eat the 3 that's left in the second hour. So we spent 2 hours at that particular power. And then for this power, right, we would eat 4 the first hour, 7 left, 4 the second hour, which means now there's 3 left, and then we eat the remaining 3, right? So it means we'll spend at least 3 hours, right? Because we eat 4 the first hour, 4 the second hour, right? And then the 3 that's left, we eat it, right? So 4 plus 4 plus 3 equals 11, which is we need a 3, right? So 3 hours. So we add all of the hours up, right? So we spend 1 hour first pile, that's 2, that's 3, 5 and 8 hours, which is good enough to eat all the bananas, right? So we return that answer, okay? So the second example is a little bit more involved, right? It's a little bit better, right? We have 5 hours, guys, right? We have 5 piles to visit, and we know we need we're gonna be spending 1 hour at least, right? At each of the piles, right? Because we just 5 piles, right? You know what I'm saying? Because we're never gonna have the case where the hour is 4, right? And there's 5 elements. It's gonna be greater right now. It's not gonna be the case, right? Because we, regardless of anything, we need to spend at least 1 hour, right, in each pile, so we can eat whatever amount of bananas at that particular pile, right? So So if we only have 5 hours and there's 5 powers to visit, that means we have to spend almost 1 hour each power, right, to fit that constraint, right? So once we have those cases, guys, we can easily say, cool, we just eat at the maximum number of, bananas at one of the maximum. So the maximum pile, right? The pile with the maximum bananas, right? So that's the speed that we're gonna eat at, right? See, well, you see 30 and you see 30 here, right? Because if we want to guarantee that we eat all of the bananas, right? And at most 1 hour, right? We just use a really large number. It could be even a million, right? That would allow us, right? But it wouldn't be the minimum one, right? We want the minimum speed that's good enough, right? And the minimum speed that's good enough to eat all of bananas, right? And at the same time, spending at most 1 hour there, right? It's the max, so it's the pile with the maximum number of bananas, right? So that's the speed that's good enough. So that means it guarantees that we spend at least at most 1 hour, right? Because the maximum one, right? We spend 1 hour there, right? And we know anything that's left, right? We only gonna need 1 hour because the number of bananas at that pile is less than my speed that I'm eating, right? So it's logically it makes sense, right? So I spend 1 hour there, 1 hour there, 1 hour there, right? Because I'm eating at a speed of 30 and 1 hour there, right? So it's very, very simple, right? But this case is a little bit different, right? We have this hour six, and uh we have 5 elements, right? So we have a little more freedom to eat at a lesser speed, right? So you see 23, right? So how can we solve these guys, right? So what we're looking for is a particular speed, right? That's kind of good enough to eat all of the bananas within that allocated time, right? How can we solve this, guys, right? So what we're gonna need to do is let's just talk about brute force, right, guys, right? The brute force solution, right? So we looking for speed, we don't know which speed that is, right? So we could try every possible speed, right? That's available to us, right? Every possible speed. And for each speed, right, we're gonna calculate how much time it takes to eat all of the bananas, right? And if the amount of time required, right, is less than or equal to the that hour, right, then we know that's the minimum one, right? So as soon as we encounter that first one, because we're gonna be starting from one to some kind of max number of speed that we don't know yet, right? And as soon as we find that speed that's good enough, right, which means that the number of hours required, right, eating at that particular speed, right, is good enough, then we simply return that answer, right? So that's why we return four, because the first one that's good enough to eat, that's a speed that's good enough to eat all bananas and still eat it within that time frame, right? So that's important. Okay, so we know that's that, right? But that's not too bad. That's the most brute force solution, right? You know what I'm saying? So, yeah. So the upper bound, right? So we know a lower bound. The lower bound will be speed of one, right? Which means because we need to, that's the slow speed, right? And then the maximum speed could be bounded by, we can bound it, saying it could be the maximum number of banana in all of the powers, right? So 11 for this case will be the upper bound, right? So we start from a speed of 1 to a speed of 11, right? Because the speed of 11 is the minimum required, right, to spend at most 1 hour each of the power, right? Because we're gonna have to spend 1 hour anyway, right? So that's the minimum speed required, right, to fit that constraint, right? So uh that's a brute force solution. I'm saying it's not too bad. It's actually a great way, to start off the problem, your interview setting, right? And it's very logical and it makes sense, right? And but we could do a little bit better, right? 'Cause we know you notice that we're searching, guys, are from one to some kind of a max speed, right? Okay, so we see that we kind of have a sorted sequence, right? A little bit, right? If you kind of think about it, right? Because we starting from speed of one, speed of two, not good enough, speed of three, not good enough, speed of four, all right, good enough. They would return four, right? So we see we're starting from a speed of one and trying all possible speed out until we get that first speed that's good enough to fit the constraint, right? So this is what we have here, right? So to make you guys visualize it even more, right? So we're going to write down all of the things, right? So let me do that real quick. All right, guys. So we have all the different speed, right, if, available. Okay. So now what we can do, guys, right? See how it's sorted, right? I'm saying because we start try one, two, nope, three, four, good. Then we return that, right? So we could do a bit better since we have a source sequence, right? We could do, when we have source sequence, what normally comes to mind, guys, right? Of course, binary search, guys, right? Binary search is the optimal solution for this problem, guys, right? And it's very logical because we have a linear search page, guys. We could apply binary search over that linear search page to find our answer, right? So it's exactly what we're going to do. So how do we do that, guys? How do we do that? We're simply what we're going to need to do, okay, is to start off applying binary search over this, right? To know which part we should discard of, right? And what kind of logic that we're going to use. Let's talk about it real quick, okay? So for this particular example, right, we see that the midpoint will be 6, right? Because our initial search page from 1 to max, right? And then we choose a midpoint, right? So if that midpoint, guys, right, that midpoint is, so if a speed, right, that particular speed is good enough, right, to eat all of the bananas, right, then we can discard of the whole right boundary, guys, right, the right side of it, because we know that the midpoint is good enough, right? Because we know the minimum one that's required, right, will be from the left boundary to the right boundary, right? So I'm never gonna waste my time searching on the right hand side, right? So that's how we can discard that, remove uh that thing, right? So this is what makes it interesting, okay? So yeah, right? This is what makes it interesting. We can remove that, right? So after we're removing that, guys, right? Now our search base is from 1 to the midpoint, okay? But we include the midpoint because it can't be the minimum one, right? We don't know yet. That's why we're gonna continue applying binary search over that, right? So we apply another binary search. Midpoint is this, right? We see that 3 is not good enough, right? So we know anything to its left, right, is gonna be useless and including itself, right? So we're not even gonna include that in our search page. We're gonna remove that, removed, right? And then we have this search space now, right, guys, right? We know that, since 3 is not good enough, right, we know that the speed that's good enough has to be, more, right? So I do mid plus 1, right, to include this search space, right? So now we apply another random search. We see that 5 is good enough, right? So I don't really need 6 anymore. And then we have 4 and 5, right? Apply another random search, then bam, we return 4, guys, right? Just like that, because 4 is the one that's the minimum one that's good enough to fit the constraint, guys, right? So this is how we can apply better search to do more, to do less comparisons, right? Which is the important, guys, right? So I'm saying, uh, instead of just checking, I'm saying instead we have a huge range, right? We don't have to iterate through everything, guys, right? We could simply apply better search and find our answer, right? So hopefully it kind of makes sense to you guys, right? The logic and why we need better search to search over that linear search space, right? That we have, right? So better search definitely is the way to go for this problem, right? So let's quickly implement that real quick. So we have our left boundary, right? Which is going to be 1. We're going to have a right boundary, guys, which would be the max, right? So, so what we're going to do is to iterate through the whole power, right? To find the maximum one. You see what I'm doing here, right? So because we need to get the upper bound, which is the maximum number of bananas in whatever power, right? So that's what it's gonna be bounded as, right? Which was the case when I talked about the maximum upper bound, right? Could be the maximum number in the array, right? Which is represents the maximum banana in the pile, okay? Okay, so what we're gonna do is the right or the max, okay? And then once we have the max, right, we have the upper bound, we can start applying our binary search, guys, right, which is important. On the left is less than the right. I'm gonna apply binary search over that search space, right? So we chose 1, guys, because that's the slowest speed we can eat at. We can't eat at speed of 0, right? So speed of 1 is the minimum one. Okay, so we apply binary search. I'm gonna apply binary search, guys. Let's quickly do that. So we're just doing simple thing that we always do, right? To avoid integer overflow. And then now this is the part where we're gonna know which part to get rid of, right? and where to go when we continue our search page, right? So what we're gonna do, guys, we're gonna implement a function that's gonna help us out, right? So we're gonna call this function can't eat it all, right? Which is gonna return a bool, right? So we're gonna pass in some parameters, right? So the parameters gonna pass is so this function, right, is going to iterate through the power, right, to calculate how much time it takes at that particular speed, right, of mid, right? Because I've always showed you guys where the speed is from 1 to the max, right? So the mid will be that current speed that we've chosen, right, which will be the midpoint. And we can also pass in the h parameter, which is the number of hours, right? So if that speed 80, so the number of hours required it takes at that speed, right? The right, if that's less than or equal to the number of hours, right, h, then that's true, right? Okay. Because let's say eating at speed of 4, right? We saw that it takes 8 hours, right? So that's good enough, right? Then I'm saying, yeah. So yeah. So we're gonna make some decision, guys. Right? If the speed is good enough, we said that just like in the walkthrough that I did before, right? So now we'll be updating the search space to be from the left boundary to mid, right? Okay. And then if that speed cannot, so at that speed we cannot eat everything, right? We're going to be moving to the right, guy, right? We can discard everything on the left side. I've already went through that in the walkthrough, right? And after we do all of that, we can simply return the left boundary when we exit the while loop. Okay, so let's continue, guys, right? We have no space for you guys, so you guys see everything, right? Public, boolean, can, I'll just copy that. All right, we're gonna pass in some parameters. So the parameters that we're gonna pass is the piles, speed, right, and inch, h hours, right? So we're gonna initialize hours spent, right? And we're gonna do the same thing that we did in the walkthrough, guys, right? We iterate through the whole thing for each pile. Okay. So each pile, let's calculate how much time it takes, right? And then we're gonna add it to the hour spent variable that's gonna help us, right? So we're gonna map that ceiling, right? And so how much time is gonna take, right? Will be the number of piles, right? And divided by the speed of that, right? So let me just make sure you guys understand. So for this one, right, we would do the pile, which is just 3 bananas there, right? And then eating at a speed of 4 would give me, 0 might say 0 because integer, right? But we're gonna cast it to a double, right? Make sure we account for that, right? We're gonna cast it to a double. Make sure we get some kind of a decimal, right? And then we're gonna 3 divided by 4, which is 0.75, right? Then we just round it to 1, right? Because we're gonna be spending 1 there, right? So 1 hour there, okay? All right, so we get that covered. So after we do that for every pile, right, we do the same calculation, right? So the number of bananas at that pile divided by the speed, right? We get a decimal, right? And then we do the ceiling of that, right? Okay. Then what we're gonna do is the hour spent. Is it less than or equal to h, right? That means that at that speed, right, the hours I spent, eating all of the bananas, right, is less than or equal to h. Then that's a good one. Then I could, return true, right? And so then all right, looks good so far, guys, right? It looks like everything's correct. So let me see. I meant to say pile. Sorry, guys. Well, it looks good so far. The logic looks sound. So we initialize our bounds, the left-right boundary. We apply binary search over search space, right? Which is from 1 to the max number of banana and 1 pile, right? And then we discard the left or right boundary depending on if we can eat it all or not, right? Okay, so let's press submit. Amazing, guys. We were able to pass all the test cases, guys. So I want to thank you guys for taking the time to watch this video, guys. If you guys found value, make sure to give me a like. If you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.